Let me introduce you the first speaker here, Jesse Davis, who's going to talk about what is async, how does it work, and when should I use it. He's leading several open source projects, including Motor, which is an async MongoDB driver for Tornado. Also, Toro, a library of locks and queues for Tornado coroutines. And let's welcome him.
Thank you. Hi, everybody. It's so exciting to be here and to be welcomed so far from home. Really far. So I work for MongoDB in New York City. And if you've been to New York, you probably know that we eat 3 kinds of food there. We eat submarine sandwiches, pizza by the slice, and the trendy new thing is called omakase, which is when you go to a sushi restaurant and the chef just gives you whatever is good that day, whatever the chef's choice is. So New York is a crowded place, and each of these 3 kinds of restaurants needs to serve lots of people, but each one faces a different sort of scaling challenge. So, for example, if you want a submarine sandwich, the process goes like this. You go into the restaurant, and the sandwich maker comes out of the back, and you go to the counter, and you tell the sandwich maker what kind of bread you want, what kind of ingredients, and you have this one-on-one synchronous interaction until the sandwich is complete and you walk away with it. So, and then the sandwich maker returns to the pool. So if you want to scale up a submarine sandwich store, you have 2 options. You can either make the sandwich maker work faster, or you can add more sandwich makers until you run out of space behind the counter. So this is like a web application with no database, no I/O. It's bound by the speed of its CPU. This might be a cryptographic service that signs requests or does some other sort of heavy computation. You can make your processors faster, or you can add more processes until you have as many processes as you have CPUs. But then you're done. And there's no point using async for this. There's no point having the sandwich maker switch off and try to make multiple sandwiches at the same time, or take a break, right? The sandwich maker should work on one sandwich at a time from start to finish. So this is when not to use async. But sandwiches aren't the only kind of food we have, right? We also have pizza. So if you want a slice of pizza, you go to the pizza place and you tell the cook what kind of slice you want. And the cook takes the slice out from behind the counter and puts it in the oven. And then you both just kind of stand around for a couple of minutes waiting for the slice to get hot. And then once it's heated up in the oven, the cook gives you the slice of pizza and you walk away happy. Now, in this case, what happens when lots of clients all show up at once? How do you scale up a pizza restaurant? Well, you don't want to add more cooks, right? That's useless because the cook is spending most of the time waiting for the slice in the oven. So it would be a waste of space behind the counter if you had 1 cook per client. You would run out of space behind the counter before you run out of room in the oven. So this is like a web service with a database. The clients arrive, the web service makes database queries, and then it waits for those queries to come back from the database. It's not spending most of its time doing computation. It's spending most of its time waiting for the database. And so having a process per client or a thread per client is a waste of resources because those processes or threads spend most of their time waiting for the database. Better to have an asynchronous process that is capable of responding to clients as they arrive and then completing requests as queries complete on the database side. In that way, you'll minimize the resources that you spend waiting for the database. And this is even more true of omakase. So when you want some sushi, you and your friends come to the sushi place and you sit down at the counter and the waiter tells the kitchen that you've arrived. And then the kitchen just starts making sushi. And as sushi dishes are completed, the waiter brings them to you and your friends at the counter. So once again, if you wanted to serve sushi to lots of people, it wouldn't make sense to have a waiter per client. You would run out of space behind the counter. It's better to have an asynchronous waiter who can deal with sushi dishes as they become ready and bring them to the clients at that time. Having a waiter per client would waste space behind the counter. And this is like Gmail or Twitter.com. Any real-time web service where you have events coming from the server to the client over a WebSocket. So when you go to Gmail, your browser opens a WebSocket to one of Google's servers, and then nothing happens. That connection sits idle, waiting for something to happen on the server, like a new email arrives for you. And then that notification comes from the server to your browser, and the browser updates itself. Now, it would be extremely wasteful to devote a thread or a process per client because it would be idle almost all the time. So it's much better in this case to have an asynchronous process where a single process can serve thousands and thousands of clients and only deal with the ones that actually need to have their needs addressed right now. So this is like the killer app for async. So that's what async is for. It minimizes resources per idle connection. It waits for things to happen cheaply, and the main resource that it needs to minimize is memory. There's an excellent discussion of this. It's a paper called the C10K paper. It's about 8 years old. It's by a guy named Dan Cagle. It's still very relevant today. Cagle coined this term for 10,000 concurrent clients. And he wrote that it's time for web servers to handle 10,000 clients simultaneously. Don't you think? After all, the web is a big place now. And he goes on to say that perhaps in the not too distant future, those who prefer using one thread per client will be able to use that paradigm even for 10,000 clients. Nevertheless, at the current time, if you actually want to support that many clients, you're probably better off using some other paradigm. So that other paradigm is a more efficient means of handling 10,000 concurrent clients, and that is async. So if async is so great, and if the kind of applications for which it's great are more common these days, why do most people still use multi-process or multi-threaded web servers instead of async? I think it's because async is hard. It's hard to code. So the problem that any web server needs to solve is that when a client request comes in, and then the web server makes some kind of request to the database or some kind of backend, it needs to store state while it's waiting for that I/O to complete. And this is even more true of WebSocket applications like Twitter or Gmail. When a client connects to the server over a WebSocket, the server waits indefinitely for some event to occur so that it can notify the client. So it needs to store state for forever, potentially, and it needs to do so very efficiently. So the traditional way of storing state while you're waiting for I/O is with a thread. So this is the only code example that I'm going to show. And the idea is to show you what it would be like to use the multi-threaded blocking style of I/O to implement a blog using Python and MongoDB. So you start off, when the application begins, you make a connection to MongoDB over the localhost connection. And then whenever a client connects to you, you call show blog posts. And this creates a cursor over all of the blog posts, most recent first. And then it actually does the I/O. So it makes a list of all of the blog posts, and it blocks while it's waiting for that result from MongoDB. So the result of the I/O is the return value of that function call. And then you can render the template and finish the request. You don't have to think about how to store state in this style of coding. It's done for you. It's in, where is it? It's in the program counter. It's in the local variables. It's in the current stack frame. That's where the state is stored when a thread is waiting for I/O to complete. So it's built into the language for you, and you already know how to do it without even thinking. It's a lot harder when you go to the asynchronous callback style. So this is using Motor. That's my non-blocking driver for MongoDB that I wrote last year. And it starts off the same. You make a client connection. But now, whenever a client requests the list of blog posts, you create a cursor, the same as before. But when you want to do I/O, you have to pass a callback. And that callback is going to be executed with the result of the I/O once it's complete. And that happens down here. The results of the I/O are passed into the callback, and then you can finish the request. So it's all very manual here. You have to express what you're going to do next manually with a callback instead of relying on Python itself to remember what it was going to do with the program counter. Your local variables and your stack frame are both gone after the I/O is complete. You need to remember what you were going to do and store all of your state by hand. So this is why async is relatively difficult to code. And I would say that in this kind of spectrum, threads and callbacks are at two extremes. Threads are very easy to use for web programming, but they have a large overhead. Whereas callbacks are relatively difficult to use, but they're extremely low overhead. There's almost no memory spent on storing a reference to a callback. These two extremes are not your only options. You also have Greenlets, which is what Gevent is based on. It's a Python extension module. There are coroutines, which are based on generators. If you went to Tzu-Ping Chung's talk yesterday called Yielding a Tulip, that was all about this topic. And I wish I had more time to talk about coroutines today, but I'll have to defer to Tzu-Ping on that one. The point is that there are a lot of compromises in between these two extremes, and there will probably continue to be more research in this area because there's no one compromise yet that's satisfied everybody for how to store state in an asynchronous framework. So we've talked a little bit about when to use it and why everybody isn't already using async. So now we can start to answer what it actually is. So asynchronous frameworks are single-threaded. That means that they cannot do computational concurrency. But that's okay because we write Python, we have a global interpreter lock, we can't use multiple cores anyway. What async frameworks can do is that they can do I/O concurrency. They can launch many I/O operations and then wait for all of them concurrently and respond to them in the order that they complete. They use non-blocking sockets to achieve this. And a non-blocking socket is just like a regular socket, except the framework has told the operating system that this socket will be used specially. It will be used in an asynchronous style. And the framework asks the operating system for event notifications using some platform-specific facility, like epoll epoll is the Linux variant, and KQ is what you use on Mac and BSD. But when you're writing async code, you don't need to worry about this because the framework handles it for you. All you need to know is that you do operations on the network, and when those operations complete, you have a callback which is executed with the result of it. The final piece of an asynchronous framework is the event loop. And what the loop does is it uses epoll or KQ to ask if any network events have happened, and then it executes the callbacks that were waiting for those network events. And it repeats that cycle forever. So this is not everybody's definition of async. If somebody is talking to you about async, this may or may not be what they mean, but this is my definition of async. And when somebody says that Node.js, for example, is an asynchronous framework, this is what they mean. This definition applies to Node, and it also applies to the main Python asynchronous frameworks. Twisted, which is very old, Tornado, which is also a few years old, and this exciting new framework called asyncio. So I'm going to spend my final few minutes describing asyncio because it's this exciting new innovation, and then we'll review when to use it once again. So asyncio, you know, if you were at the Yielding a Tulip talk yesterday, that asyncio is a new async framework in the Python 3.4 standard library. It was written by Guido van Rossum and a bunch of other Python core contributors, including me. I wrote a little bit of it, and I'm very proud of that. It implements this PEP 3156, which is it's a few pages long, and it's actually a really good read. It describes what problem asyncio is trying to solve and how it solves it and what the specification is. Asyncio contributes a standard event loop to the Python standard library. And this is a really exciting development in Python's history. It means that, so in the past decade, we've had to continuously reinvent the wheel. Every time we want to write a library that uses an async framework, we have to write it for one framework in particular. So when I wrote Motor, for example, it was specifically for Tornado. And the problem with this is that if you now want to support Twisted, you have to start over again from scratch and rewrite it. So we keep rewriting the same code over and over for each async framework individually. What asyncio provides is a standard interface to an event loop, which means that in the near future, we can stop rewriting all of this async code and just write Python libraries that are generically async. And that use this standard interface to interoperate with all of the async frameworks the same. And it also provides coroutines, which again, I don't have time to talk about. So to wrap up, should you use async or not? It's kind of like a medicine. There are indications and there are contraindications. So indications for async are if you have a slow backend, if you're making pizza, if you're spending a lot of time waiting for database queries, then you have a lot of idle connections and you don't want to spend a lot of resources holding those open. So async is for you. Even more so with real-time web, WebSocket applications. Those are like omakase. And again, your connections are long-lived. There are a very large number of them, and they're mostly idle. So async minimizes the resources that you spend on those idle connections. And anytime you have an extremely large number of clients connected to you, async will help you scale out without spending too much memory. There are some contraindications. So one of them is if you're making submarine sandwiches. Async will not help you with CPU-intensive applications. So the additional complexity of async programming is not worth it. It doesn't buy you anything. So don't use it. Another really important point is if you don't have an async driver for some backend that you're talking to, you shouldn't use async. So with MySQL, for example, there's no official asynchronous driver for MySQL for Python. So if you're using MySQL, I would recommend against using async. Because if you use a blocking driver with an asynchronous framework, you end up in the worst of both worlds. You're single-threaded and you're blocking. And it's extremely dangerous and you'll get terrible performance. But I see people making this error all the time because they don't understand how async works. If you're using MongoDB, on the other hand, we have async drivers for all of the major Python async frameworks, so you can safely use that and get the benefits without any of the downsides. The final thing is that async is a little hard to learn. You need to be prepared to make an investment. So if you're writing an application and it needs to be done today, and you haven't spent a lot of time using an async framework, now may not be the time for you to learn. And if you're starting up a startup and you're building an app and you need to hire people, again, people will be more familiar with the traditional style than they will be with the async. So you need to be aware that you'll have to invest in training people. The good news about this is that it's not all one thing or the other. A lot of really complex web applications have both features that are ideal for async and features that don't need async. And so they can divide the application up into synchronous and asynchronous styles using the best style for each feature. As long as the two aspects are in separate processes, so you have an async process handling the WebSockets and a synchronous process handling your MySQL queries, then you can get the best of both worlds without much effort. So that's what it is, when you should use it, and how it works. And I have 1 minute and 45 seconds for questions. Thank you. In the back there, I think you can press your talk button if you have a mic, or you can come down here. Or shout.
Thank you for your talk. I have one question. Also regarding MongoDB, your library Motor, is it already ready for async
No. So the question is Motor, which was written for Tornado, is it ready for async I/O? And the answer is no. But I have plans. Watch the project later this year.
Thank you.
Thanks. Other questions? Uh-huh.
I'm using like Tornado to build a chat room app. So now the problem I'm facing is like how to each core hosts a chat room. How to get them to communicate with each other or cross-server?
Oh, I see. So the question is, if you have multiple Tornado processes running to take advantage of multiple cores, how do you share data among them? And there are a number of options, the main one being Redis, or using MongoDB and tailing the op log, which is something that I've done. But you need some central broker process. And usually that would be a database with long polling features like Redis or MongoDB, or a dedicated event queue like ZeroMQ or RabbitMQ that you would use for that.
So does it make sense to use like async IO with like Celery or RabbitMQ to combine them together?
I think so, and there's a ZeroMQ driver for async IO. But I haven't used that myself, so there may be details that I don't know the facts about. Thanks. Probably time for like one more, do you think? Okay, one more question? Whenever you say that, there's no more questions. I've done this like 10 times, and every time you say that I have time for one more questions, there isn't one. It's this magic trick. I can make you disappear. Okay, thank you very much.